Okay, so I will start with the topologist approach here again. So we so our approach is to study more general structures at developing maps that are emergence. Okay, so first of all, the Benzic and Milner show that the affinely flat two manifolds has Euler characteristic equal to zero. Okay. So of course, the higher dimensional version of this is Chern conjecture. So that's only proven for a special affine case currently, and it's still open in general. Uh, and Benzikri studied the convex domains omega that arise for convex projective manifolds, omega mod gamma. And so he showed that omega is C1 or omega is ellipsoid here. And the Nagano and Yagi classified affine structures on tori. Okay. So the basic method is that so so for each affine plane, there's some so if the holonomic is diagonal, then you can find these invariant regions and invariant lines, and you can cut this up. So the invariant planes usually have a matrix. Okay, invariant regions has metric, and then these lines can be taken inverse image into the universal cover, and then they will cover simply closed curves downstairs. Okay, so those are the first things that was done, and then Goldman classified the projective structures on tori. So basically, the important ones are when the holonomic is diagonalizable, and in that case, there's an invariant triangle and these three invariant lines, and so the developing image will go into here, and then you can show that it doesn't go to the fixed points. Okay, and so these invariant inverse images of these lines will go to lines in the universal cover, and then they will cover simple closed curves. Okay, so that will give you the decomposition. And and then there's this notion called grafting. So once you have this annuli, then so you can actually make it into compact annuli by adding the boundary. And then you can graph these into convex projective surfaces to make a non-convex projective surfaces. Okay, so because these locally, it looks like principal geodesics will have a same neighborhood, so you can cut these up and then glue these together. So the convex decomposition theorem is that if you have a cross-orientable real projective surface, sigma of negative order characteristic, then the sigma has a disjoint collection of simple cross geodesic, decomposing into some union of properly convex surfaces and annuli. So that's a theorem that I prove. And so our theorem is that if you have a close orientable real projective surface of negative order characteristic, then the deformation space is just going to be a union of countable union of cells and countable disjoint union of cells of dimension minus x to the sigma. Okay, so the basic idea is that if you have any close real projective surface, then you can so since you can obtain it by using these taking this grafting with annuli, so you can remove these annuli to make it into properly convex ones. And the properly convex projective structures were classified by Goldman, so you can use that to obtain this result here. Okay. So how did the Goldman classify the convex projective structures on cross surfaces? So the idea is that you can cut off the surface into pair of pans. Okay, so that's the elementary pieces of surfaces. So you cannot cut it up further into negative Euler characteristics subsurfaces anymore. So then each pair of pants is a union of two open triangles. So you can so it is homeomorphic to this union of two triangles. Okay. But you have to glue this side to this side. I guess this side to this side, this side to this side, and then this side to this side. Okay. So if you have this four triangle and then you identify this triangle to this triangle to this, then you get a pair of pants, okay? Or the thrice punctured sphere. Okay, and so you have any convex ones, you can also convex projective structure. You can also find these triangles. Okay, so there are of course some choices, but you have to choose the right fixed points, and uh, then you can always find these. Okay, so you need these to be the for example, the least eigenvalue of this A, and then B has this is least eigenvalue B, and so on. Okay. Okay, so that's required, and then you can put it into this standard position. Then you look at the projective invariance, and the key idea is that for the pair of pants, if you map it to the boundary invariance, so D of partial P is so partial P is three closed geodesics, and then it has projective invariance. The holonomy has some invariance, so it's classified by some two variables. Okay, so this is really a six-dimensional space, and then this is so we showed that this is a principal vibration. So of course that needs some computational work, but it's really easy algebraic solution problem, so you can solve this. But of course, some sort of geometric procedure will make it easy to solve. And then of course, so once you have this, then so you can fix the boundary invariance. And if you fix boundary invariance, you can glue these things. So as long as the boundary invariance is the same, then you can glue these back, and so then again you can show that the whole space is homeomorphic to a cell. Okay. Because this is a cell and this is a vibration of a cell. So TP is a cell, and then you have to do the construction similar to what I showed about the Thurston's work, and then you have to do some vibration over the diagonals, subspace where the boundaries are matching, and then you have to do the gluings, and then gluings are parameterized and so on. So that's how you can show these things. And then you can generalize this to two orbifolds, and so if a cross orbifold of Euler characteristic negative, then the deformation space is homeomorphic to this dimensional cell. So X sigma is underlying space, and then K sigma is a number of cone points. BC is the number of four cone points of order 2, and then KR is a number of corner reflectors, and the BR is a number of corner reflectors of order 2. Okay. So I'm doing only the closed case. Of course, if you have a boundary, then you should be able to mirror it. Okay, so then it becomes closed, and then the deformation space is actually the same. So this will give you the dimension. So when the method is just very similar to Thurston, then you decompose into elementary piece, and then for each elementary piece, orbifold, you have to do these kind of arguments. Then you have to glue these together, and then what the gluing parameters are like, and then you can show this. Okay, so that's the theory, and okay, so then we go to Hitchin's conjecture and the generalization. So you have a convex cross orbifold or surface or orbifold of form omega minus gamma with negative order characteristic. So then there is a representation determined only up to conjugation by PGL 3R. And this gives you a map. So you have a deformation space and go to the character variety, so we say variety, but it's not a variety in the algebraic geometry sense, of course. So this map is known to be local homeomorphism. And this, I mean, for this cross case, these are always land in home plus. Okay, so it's actually irreducible part. So you don't have to really worry about the non-Hash GIT quotients or this kind of thing. So it will be local homeomorphism. So that, but this map is actually homeomorphism into the Hitchin-Teichmüller component. So there was a Hitchin-Teichmüller component in here, Hitchin component in here, so it will be homeomorphism. So the main idea is, of course, is local homeomorphism, right? So it has an open image, and so you just have to show its image is closed, and of course the closeness is just a bit of an argument with how the convex domain has to converge. And of course, there's some sort of Euler characteristic argument that you need to get to show that it cannot this domain cannot degenerate into a line or a big half space or that kind of thing. So that was the basic key idea here. And of course, Kapovich has something to do with this part, but he wasn't really included in the authors. And then of course, and also the Wilson also, right? And for n equal to 2, this is a classical theorem due to Wire. So Wire showed this kind of thing for SL2R, PSL2R in the first forays for the Teichmüller space thing. And of course, Goldman was able to generalize this to all the to show for all the components here. But that's his thesis work a long time ago. Okay. So now we can actually generalize this to dimension n is bigger than or equal to 4. Okay, so what he said was Hitchin representation is he defined it as a representation which can be deformable to function representation. So those in Hitchin-Teichmüller component. So I said Hitchin-Teichmüller, but it's really the Hitchin component. Okay, so I'm just saying Teichmüller because it's sort of added for information. Because we don't map up by the mapping class group, that's why. So the basic theorem is that so if it's a Hitchin representation, there is a unique row equivariant hyperconvex curve, which is actually the limit curve. So if you have any hyperbolic group, then there is a Gromov boundary. So in the surface case, this is just a circle. So there's just this circle, which is the infinity of the function group. Okay, and then this maps to RPN minus 1, and this curve is continuous curve, and it's called hyperconvex. So if you for any n distinct points. This is a direct sum. Okay, so up to n, right? So you have this dimension n, right? So for convex curve in RP2 is of course any 3 of them has to become independent. So this is really a condition about independence of you choose any endpoints. These are all independent. That's the point here. So he showed that this is a hyperconvex curve, and so the basic idea is that so if you just send in the PSL2R to PSLNR in the irreducible form, then this PSL2R acts on this hyperconvex curve, which is smooth in the beginning for this function one. And then as you deform, you can keep showing that there's some anosov condition that will give you these, keep preserving these kind of circles. So now it may not be smooth, but it will become only continuous. Okay. So so that's a sort of a generalized version of convexity. Okay, so it's now before it was preserving a convex curve. Now it's preserving a hyperconvex curve. Okay, and so now you can show that every Hitchin representation is discrete phasable and purely loxodromic. So so discrete faithfulness comes because this action on this, if you look at the group action on this circle, so PSL2R will in this representation image will act on this limit circle as well, right? And then these circles action is like the how the function group acts, and then so you can see that it's really conjugate to function group action up to some continuous conjugation. And so that's how we show is faithful and purely loxodromic because so for at each point there's actually going to be some sort of flag, and actually in this case even a frame is going to be preserved, and so it's always completely diagonalizable with positive eigenvalues which are different. Okay, so purely loxodromic means that kind of thing. And then the mapping class group acts properly on this HN. Again, so that's again following these ideas. So this is quite a good work. And then another thing is the work of Benoit. So Katz, Spinberg, and Kozul studied the study of deformations of representation dividing a properly convex domain in RPN. So if you have a properly convex domain, when I say dividing, it means that it acts discretely and the quotient is compact and Hausdorff. So that's what this is. And so to get more of such action is to do the bending. So if the manifold has some sort of totally geodesic submanifold in it, then you can do reglue these. You cut it up and then reglue using some diagonal automorphism to get another convex projective surface. I mean manifolds or orbifolds. So I mean, so the thing that was done by Johnson and Milson, and these were you can so sometimes you can show that these deformation space is actually singular because sometimes there are some these cross these totally geodesic sub hypersurfaces may meet, have many of them, and may meet in the weird way. And then if you meet three or more meets, then these will be singular. Okay, so they also worked out for conformally flat structures. Okay, so these are usually arithmetic examples, and so Johnson and Mason found many of these examples, and also this is a good reference for character varieties. So what Benoit did was to show that if gamma is a irreducible tangent-free subgroup of PGL-MR, and then gamma X properly on an actual properly convex domain omega if and only if gamma is positive proximal. So positive proximal means that the largest eigenvalue has a rank is multiplicity 1, and not largest it is the largest norm, and the largest norm has a multiplicity 1 also. That's the definition, and so the largest norm eigenvalue is positive and has multiplicity 1 here. So then acts divisibly on strictly convex omega, and if omega is not the interior of ellipse, so then the gamma is Zariski dense in PGL MR. Okay. Okay. So then next, if gamma is let gamma be a discrete torsion-free subgroup of PGL-MR dividing an open properly convex domain in RP m-1, and C is corresponding cone in RPM, then one of the following holes. So either it's a product which is reducible, so it's going to be a sum of two cones or something like this, or it's homogeneous, or gamma is Zariski dense in PGL MR. Okay. So it's going to be reducible cones, which means it's a sum of two independent cones in two independent subspaces. Okay, so that's what this showed, And also, if the virtual center of gamma zero is trivial, so virtual center, I mean that it's so it's a uh, center of some finite uh, index subgroup. Okay, if you can find such a finite center is trivial for some finite index subgroup, then the set of these images of rho which dividing the convex open domain in RPM minus one is closed in this home space. Okay, so it's a sort of a closeness condition. So so as long as a group doesn't contain some large center here, then you can show that the set of representation dividing the convex open domain is closed. And of course, so that's generalizes our theorem for surfaces. You know, okay. And the openness was obtained by Kuzo, and let gamma be as above, then the following conditions are equivalent. So omega is strictly convex, boundary omega is C1, and gamma is Gromov hyperbolic, and geodesic flow on omega mod gamma is and also okay. So that's his additional work that for the word hyperbolic ones, these are always strictly convex, and the group has to be Gromov hyperbolic. Okay, and that's associated with this geodesic flow being also. So it will have a geodesic flow because it's a Finstra geodesic Finstra manifold will still have a geodesics, and then there's a geodesic flow as well. Um, so this exploits the fact that the space is more or less like negatively curved in the Riemannian sense. Okay, so it's a sort of analog of that. Yeah. Okay, and so we want to get more close convex real projective manifold. So the Coxeter orbifolds, usually I mean the close ones admitting hyperbolic structures have finite cover that are manifolds. So some of were based on truncation polytope, and so many of these are deformable, and you can compute the dimension of the deformation spaces. So these were studied by Bimberg and so on. And so the Coxeter orbifold case is the most simplest ones you can start studying on this kind of topic. But for hyperbolic three manifolds, of course, it determines a discrete faithful representation to PSL2R, or you can consider these as SO plus 3-1. So here I mean by SO3 plus, I mean that it preserves the upper cone, and S means that it has determinant one. So then this representation is unique up to conjugation by most rigidity, and so Cooper, Long, and Thistlethwaite they show that so when you consider these subgroups, PO3431. So suppose you want to now go to SL4R, then so there's a list of hyperbolic three manifold, closed hyperbolic three manifold by built by Hudson and Weeks. And so you take about 5,000 of them, and then 5% will admit some non-trivial deformation into SL4. So it will become projective. I mean, which is not coming from the hyperbolic ones. So each representation variety then gives you a family of convex real projective structure on the manifold. Okay, so 5% is actually sort of bigger than what people thought, because so for conformal ones, this is really small. Actually, people don't even have an estimate. Okay, so so that's the and then the next, there were some results on Dane surgery. So Hosner and Porty, they show the projective rigidity of infinitely many hyperbolic three manifold obtained from Dane surgery from infinitesimally projectively rigid cusp hyperbolic stream manifold. So you have some cusp hyperbolic stream manifolds, and then you can show that it's projectively rigid relative to the boundary. So there's some 8 cohomological condition. So once you have that, then so if you do any surgery on them, so infinitely many of them will be projectively, I mean, rigid. So you cannot deform from any to any non-hyperbolic ones once you stop from hyperbolic ones. So these apply to some tunnel number 1 knots, and then so still the remaining thing is calculate the dimension of real projective structure on knot complements and relate the results to CLT. So we still have not been able to do that completely yet. Okay, so this ends the first half, and then we'll do the end next time. Right?